The types of bonding present determines the behaviour and properties of substances. Usually this is easy to predict. The challenge to students studying chemistry is investigating and explaining what happens when those predictions prove incorrect. In this 3-minute lesson, we look at anomalies in the types of bonding expected and how these help us better understand the concepts of bonds and bonding. We can predict that the outer electrons in atoms on the left and centre of the periodic table may transfer to atoms on the right side of the periodic table, forming an ionic bond. Simply put, metal atoms combine with non-metal atoms to form ionic compounds. But let's look at beryllium chloride. Beryllium is a group 2 metal and would be expected to lose its 2 outer electrons to 2 individual chlorine atoms. The tiny beryllium ion can approach an outer electron pair on the chloride ion, inducing an electrostatic force. The electron pair is effectively shared between the beryllium and chlorine nuclei, forming a covalent bond. This is confirmed by the covalent behaviour and properties of beryllium chloride. A similar observation is made with aluminium chloride, which is also covalently bonded. In a previous lesson, we described how differences in the electronegativity of covalently bonded atoms produced a dipole or polar bond. This can lead to the formation of molecular ions, that is, a covalent molecule with an overall net charge. For example, water molecules undergo protonation, forming the hydroxide ion and hydronium ion. This is called the self-ionization of water. The process happens more readily when certain molecules, for example hydrogen chloride, are mixed with water. The resulting dissociation of hydrogen chloride molecules to form individual ions in aqueous solution leads to acid-base behaviour. Hydrogen chloride dissociates, donating a hydrogen ion or proton to a water molecule, thus behaving as an acid. A similar process is observed when ammonia molecules mix with water. The ammonia molecule accepts a hydrogen ion or proton from a water molecule. In this instance, ammonia is behaving as a base. Bonding behaviour is influenced by electron charge density, which is determined by the size of individual particles and their overall charge. Small particles with a large charge have a higher charge density than larger particles with a small charge. Let's compare the bond behaviour of group 2 carbonates. Barium carbonate is a thermally stable ionic compound. The large barium ion has a much lower charge density compared to the smaller magnesium ion. The magnesium ion can influence the electrons on one of the oxygen-carbon bonds, leading to thermal decomposition on heating. The solubility of ionic compounds can partly be explained by the relative charge density of ions. Ions with a single charge tend to be more soluble than ions with a greater charge. For example, group 1 metal ions and nitrate ions are soluble in water, while the solubility of group 2 metal ions and carbonates tend to be less soluble or even insoluble. The solubility of ionic substances is determined by how charge density affects the relative strength of ionic lattices compared to the strengths of ion dipole bonds formed in aqueous solution. In the next series of 3-minute lessons, we shall be developing ideas on the behaviours of acids and bases.